Starting the class, children. So we are starting new unit, kinetics. I think I gave you some introduction in the last class. So what is the meaning of kinetics in chemistry? Any one of you? Chemistry, kinetics. What's the meaning? Yes, Yusuf. What is the meaning of kinetics in chemistry? Kinetics means rates of reaction. Speed of the reaction. Yes. Rates. Rate of reactions. And what is the meaning of rate of the reaction? That how fast and slow. So you can say speed of the reaction. Speed of the reaction. And what is the meaning of speed of the reaction? Or the rate of the reaction? It means that how fast and slow the reaction, fast and slow. So when I say these words, fast, slow, speed, then it means we are measuring the change in the reaction with time. That how much time the reaction is, the change in concentration or the formation of the product or consumption of the reactant in the given amount of time. So that's the meaning of the rate of the reaction. So you will measure, you will perform the experiment and you will measure the change in the rates of the reaction, right? You will measure the change in the concentration of the reactants or products with time. So the rate of the reaction, so please all of you type here, rate of the reaction means how fast or slow is the reaction. Some reactions are very explosive because in that case, the change in the concentration of the reactant per unit time is very fast. Within seconds, the reaction is taking place. So all the energy which is liberated is taking place in less time. So it becomes explosive. Some reactions are slow. They may take some time, but some reactions are very slow. There are reactions which need years and years to take place. So those reactions are very slow, but they are also happening. So reactions very fast and very slow that you are going to learn in this unit. We're okay with this? So now let's define the rate of a reaction. So the proper kinetics starts from here. Rate of the reaction. The reaction rate by definition is the change in concentration of the reactant per unit time. But as the concentration of the reactant changing, what happens to the concentration of the product? Let's say I started with A initially. I'm writing here, children. A initially giving me B. I started initially. Remember I told you about initial final. Initial, let's say there is 2 molar of A and B is 0. And finally, after let's say 5 seconds, after 5 seconds, because we are dealing with kinetics. Now I will start talking about time. Jyoti, Atharva, Partha, Sami, please start answering here my questions. This time you promised me that you are going to learn totally here. So whatever you are learning, new things, you are going to type it here. Let's say final is 1 molar. If this 2 molar has become 1 molar, then what is the amount of B formed? 1 molar, very good. So as the A decreasing, what is happening to B? What is happening to B? Increasing. This decrease and increase is 1:1 because the coefficients are 1, 1, right? This increase and decrease is 1:1. You're getting it? So we can define the rate of the reaction As the change I'm going to represent with delta. Concentration of the reactant, which I'm going to say A, my reactant is A, per unit time with time over delta T. But this concentration of A is decreasing, so I will put a negative sign. And this is called as rate of disappearance of A. This is rate of disappearance of A, which is actually equal to rate of appearance of B. Am I right? Because they are 1:1. See, if one A disappears, one B appears. So it is equal to rate of appearance of B. So please write down these two words. Disappearance of the reactant, rate of disappearance of the reactant, rate of appearance of the product. So what is the meaning of negative sign here? Negative, children? Yeah, please type it here. It means, yes. What is the meaning of negative sign? Can you type it fast, children? Save my time. All of you know it? Yes, Yusuf. It means the concentration of A is decreasing. Concentration of A, Jyoti, is decreasing. Rate is not decreasing. Which variables? Delta A and delta T. This one. So delta A, read this definition. Can you see that you started with A, the black one? All these black. Now you are measuring after 10 seconds. Let's say this is 10 seconds. Can you see amount of A has decreased and some amount of B is formed? You measure this change. So that will be delta A. Measure the change in amount of A. And this is happening within 10 seconds. Measure the time taken. The ratio of change in amount with time is the rate. And because this is decreasing, so I have to put negative. Do you know why we are placing negative here? Because by definition, delta means change. And delta is always defined as concentration of A final minus concentration of A initial. Now this value, if you look at here, this is A when the time is 0 and this is A when the time is 10 seconds. What is happening to A? Initial, final. Which one is more? Final is more or initial is more? Final is less, initial is more. So it means this delta A is negative. Negative, right? This answer will be negative, correct? But rates, we don't have rates as negative. We can have decreasing rate, increasing rate, but we don't have that the negative concentrations. I cannot have this negative concentration here. Agreed? No negative concentrations. So that is the reason, by definition, they have included a negative here. So this negative and this delta A is negative. Negative, negative will become positive. Your rate will be positive. Is it okay? You're understanding the meaning of negative? Any question, children? Because after that, I'm going to show you some questions. So this is what we defined. Can you give me the units of rate, children, from this definition? Units of rate is concentration over time. Yes. Concentration units are molarity. Time is T in seconds. So molarity per second. So it depends. If you're taking molarity, time in seconds, molarity per second. If you're taking time in minutes, hours, days, years. So that will be the unit, right? Or you can say molarity as moles per liter per second. You can say this also, right? And you can say this also. You will see many chemistry books are writing like this. Mole, liter, 1 liter is 1 dm cubed. We did it in unit 0. 1 liter is 1 dm. So they use this unit also. But AP is more into this, more into liter. IB chemistry, if somebody is doing IB chemistry, then dm cubed. But meaning is same, right? So is the unit of rate is clear? Fine. This is important that you should know units of rate. So in whatever way you are measuring the change in amount, right now we are defining it as the change in concentration, but there are questions in which you are measuring the change as change in grams. How many grams of the reactant are consumed in 10 seconds. So you have to read the question carefully and then from there you will decide the unit. Children, we are good with this? Okay. Okay. I think I have to write down an equation here. So I'm going to discuss one reaction. Please ignore this reaction. Look at this reaction. We did this reaction first. And here you defined minus delta A over delta T, the change in concentration of A per unit time is plus delta B over delta T that we have defined, children, right? This we have defined. Here this is 1 is to 1. What is it called as? What is this called as? Rate of disappearance of A. What is this called as? Can you type it here, children? What I'm saying? Rate of disappearance of A. Rate of appearance of B. Yes, Sanvi. And this is appearance of B. Yes. Disappearance and appearance. Yes, yes. Good, good. Dhruv, you're there? Your answers are not coming. Then A, if the reaction is like this, the rate of disappearance of A is still defined as minus delta A over delta T. The rate of appearance of B is still defined as delta B over delta T. Yes, yes. So sometimes, see, Sanvi is saying that this rate of appearance, disappearance. So it depends. If you are talking in terms of the reactant, you will use this equation. If you're talking in terms of the product, you will use this equation. So here also rate of disappearance of A is this, rate of appearance of B is this. But are they equal, children? Is the rate of appearance of B exactly same as A? So can I say the rate of appearance of B is double of A? But if I want to put them equal like this, so don't you think that I have to divide the rate of appearance of B by a factor of 2? Means if let's say rate of appearance of B is, I'm giving you one uh, question here, understand that. I'm saying during this experiment, we observe the rate of appearance of B as 2 molar per second. You're understanding the unit, children? For this reaction. So what is the rate of disappearance of A? Is it same? Is it same in this reaction? No. So what is it? 1 molar per second. Because appearance of B is twice. So that's why whatever the rate of appearance of B, which I gave you here, you have to divide it by 2. Right, Dhruv? Okay. Sammy? 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 You have not even typed one answer. I'm checking your chat. I'm getting chats also saved with me. So if you people don't listen to me, don't answer here. Oh, he answered once. Yeah, good. Good, Sammy. I can share the chat messages also. It's not a warning I'm giving you. No, nothing like that, children. I know that you are very nice students and all of you are doing good. It's just I'm saying for fun. So don't worry, I'm not going to share anything like that. Okay, so we are good with understanding of this concept. Okay, now if you have understood this and you agree that if there is a reaction, this reaction, A giving you 2B, then rates of appearance, rate of disappearance, this is negative, rate of disappearance, rate of appearance, they are 1 is to 2, right? So appearance, you have to divide it by 2. Exactly in the same way, we can write here rate of disappearance of A, that is this, is equal to rate of disappearance of B, right? Divided by 2. Agreed? Because this is double. Children, you are understanding this? Which is equal to rate of appearance of C divided by 3. See this coefficient? Because it is appearing 3 times than that of A. And these two are in the ratio of 2 is to 3, which is equal to rate of appearance of D. So in simple language, you take the coefficients 1, 2, 3, 1 here in the denominator and raise they will become equal to each other. Can I give you one question here, children? Ready for the question? This one is negative. If the rate of disappearance of B is 6 molar per second, this one, disappearance, this value is 6 molar per second. Can you tell me what is the rate of appearance of E? See, rate, this number will not be negative. Okay, understand that. Rate will always be positive. So what is the rate of appearance of E? All of you please answer it. Rate of appearance of E. See how are they related? Yes. So rate of appearance of A will be 3 molar per second. What will be the rate of appearance of D? Sanvi, Sammy, capital M. Oh yes, rate of disappearance of A. Yes, Dhruv. Thanks for correcting. It's the rate of disappearance of E. What is the rate of appearance of D? Appearance of D. This one. 3 molar per second. See, relate them like this. Yes. Partha, good. Now, can you tell me the rate of appearance of C? Can you give me the rate of appearance of C? Okay, how come it is 9? So rate of appearance of C, just rearrange this equation. This 3 will come here. It will be 3 over 2 minus delta B over delta T, which is given to you, 6 molar. So 3 times 6 divided by 2. So Sanvi is right. Partha is right. No, Atharva, it's not negative. That's what I was saying. I was telling you. This negative is used so that this decrease in concentration, if it gets a negative sign in your calculation, that negative and this negative will become positive. Because it is the rate of disappearance. Rate of disappearance by definition is this. This negative is included in the definition. That value is 6 molar per second. So just ignore this negative here, right? By definition, rate of disappearance is this, and the value is this. The value is not going to have negative because this negative and the change in concentration, which is also negative, will make it positive. Yes, yes, Sanvi. Yes. Sanvi is writing it, Atharva, in a very good language. I hope, is it clear now? Because the change in concentration is negative, because it's decreasing with time, that negative, this negative will give you a positive value of the rate. Okay, good. We are good, children? Ready for more questions? All of you? Okay, Sammy, Partha, Yusuf, read this question carefully. A certain experiment over a specific period, 0.0048 mole of the pH3 consumed, means decreasing, in a 2-liter container each second. Because this is the reactant and it is consumed, so can I say minus delta pH3 over delta T is how many moles are consumed? These in 2 liter each second. So what's the molarity? Change in molarity. 0.0048 divided by 2. That's the molarity. Every 1 second. Can you see this, children? So what is this? 0.0024 molar per second. Oh, you people are already answering it. What is this, Partha? 0.0012? Don't divide it by 4, okay? This is the rate of disappearance of pH3. Is 3. Now they are asking what is the rate of formation of P4? Means delta P4 over delta T. And that you know is 1/4, because this is appearing 4 times, 1/4 of minus delta pH3 over delta T, which is equal to 0.0024 divided by 4. Everybody okay with this? Yeah, Yusuf is already doing it. Good, Yusuf. Units same, molar per second. So I'm sure you can handle this part. H2. H2 is here. You can work H2 with P4. H2 will be 6 times of P4, isn't it? H2 will be 6 times of P4. P4 you worked out as 0.0006. Take care of the sig fig. How many sig fig in this number? 2. How many sig fig in this number? 2. So you are going to say your answer as 0.0060. molar per second. No, it was the rate of dissipation. I'm answering question asked by Sanvi. You're talking about this one. This is the rate of disappearance of pH3. Yes. Then rate of appearance of P4 is this one. It is 1/4 of pH3. See, for every 1 mole of P4 formed, 4 moles of pH3 are consumed. And this is the rate of appearance of P4. Okay, now the next is H2. So you can do H2 like this. Rate of appearance of H2, this one, they are asking this, is equal to, now you are going to put this value, negative delta pH3 over delta T, but they are not equal to each other. See 4 and 6. So take 1/4 here. You're getting it, children? Take 1/4 here and take 1/6 here. So it means rate of appearance of H2, this one, is 6/4 minus rate of, see this one, can I say that? And this value I know, where? This. So answer is 0.0024 times 6 divided by 4, which is two significant figures. Units. Is it okay? There is one more way of doing it. You can relate these two. Can we do this? I'm doing it here. See, you have the rate of appearance of P4, this one, rate of appearance of P4. So can you see that the rate of appearance of P4 is equal to 1/6 rate of appearance of H2? The rate of appearance of P4 we calculated 0.0060. Now I want to calculate the rate of appearance of H2. So multiplied by 6. This 6 will come this side. Is rate of appearance of H2. You're getting exactly same answer. This is exactly same thing. 0.0036 molar per second. Children, this question is very important. It's a multiple choice question, but it's very simple if it is very clear in our head. We are relating the rates of appearance and disappearance using the coefficients of the balanced equation. Anyone has any problem? Sammy, did you answer any question? Sammy? Partha? Sammy, you're understanding this? Please answer fast. So why you're not answering any calculation, any part? You're not answering anything. Okay. Ready for next question? Sammy, this time participate, okay? Don't worry if you're wrong. We all are here to help you, okay? Answer the next question. Exactly similar question. Can we do this? Read the question. Sammy, read the question. These two are disappearing. This one is appearing. Rate of disappearance of N2 means, please write down in your notes because it's difficult to type it here. N2. Are we okay with this? This is the rate of disappearance of N2. What is the rate of disappearance of H2? This is the rate of disappearance of H2. What is the rate of appearance of NH3? This is the rate of appearance of NH3, change in concentration of NH3 per unit time. Are they equal to each other? Are these rates equal to each other? No. So, no, it will not be in the formula sheet. It's a basic understanding of kinetics. So, can I say the rate of disappearance of N2 is, yes, 1 over 3? Because rate of disappearance of H2 is 3 times more than that of N2. And this 2 will come here, 1 over 2. Is it okay? Partha? Children, this one is okay? That's the question. What's the relationship between the rate of production of ammonia and the consumption of hydrogen? So they are talking about this. That's the relationship. Yes. The rate of formation of ammonia will be 2/3 of the rate of disappearance of hydrogen. Answer a question, Semi. Again, your answers are not coming. Only yes is coming. Semi, please. If I say the rate of disappearance of H2, this is minus, is 3 molar per second. Can you give me the rate of formation of ammonia, children? Answer it very fast. Rate of formation of ammonia. Mhm. This value is given to you, this one, as 3. So it will be 3 times, this 2 will come here, 2 on this side, divided by 3. 3 cancelled. It's 2 molar per second. Yes, yes. Yes, Sammy, very good. With the units, perfect. Can you work out the rate of disappearance of N2? Yes, rate of disappearance of N2 will be 1/3 of the rate of disappearance of H2. So it will be 1 by 3 times 3. Can you see the value is still positive? I'm not writing negative there. So with the rates value, ignore minus. That is already compensated in the calculation part. We are good with this type of questions? So that is the unit 3. We are doing unit 5. In unit 5, this is your topic 6.1. Okay, now let's continue with this. Now let's do the graphical representation. You will see plenty of graphs in this unit. That is the reason I gave you so much time about graphs in unit 0. So I'm expecting that now you can understand these graphs very fast. Can you see the data here? Time versus concentration of Br2. So there is a reaction we are carrying out. In the reaction, this is Br2, right? And there is a change in concentration of Br2 with time. And the data is there, experimental data. This is experimental data. We are performing an experiment. There are different ways of measuring the change in concentration of Br2. Br2 is a colored liquid, colored. Colored means you can use that B.S. Lambert's law spectrophotometer. You remember that? We did one in unit 3, something like 3.10 or 11. B.S. Lambert's law, how to calculate concentrations of the colored solution. We were making the calibration curve. In unit 3, we did that, right? So we can use spectrophotometer that can tell us the concentrations at different time interval during the reaction. Okay, so you have to visualize all these things. So I think in my notes is mentioned also that we can use spectrophotometer here because it's a colored compound. Make a graph, the graph of concentration of Br2 with time. This is the concentration of Br2 here on the y-axis, and this is time. So what is happening to the concentration of Br2 with time? What is happening? The concentration is increasing or decreasing? Is decreasing. What is the slope of this line? Slope, if I say, by definition, slopes are delta y over delta t. What is delta y? Delta Br2. Y is this over delta t. Now this is decreasing, so if you calculate, you will get a negative sign. This negative. This slope is not constant. Can you, and this slope, by definition, what is it? Rate of disappearance of Br2. This is rate of the reaction. This is rate is equal to rate. And you can see they are calculating the slope at different time interval. What is happening to the slope? Is it constant or changing? It's changing. Is it increasing or decreasing? Children, the slope, the rate, is it increasing or decreasing? Mm-hmm. It's decreasing. Only one student? It's decreasing. Now the question is, the rate is not constant. When I started the experiment, you can see the slope is very high, high slope. A fast decrease initially, a fast decrease in the concentration of Br2 means in less time, more decrease. This is a steep slope, means more decrease in less time. Then you can see here, finally, the decrease is slowing down. It's becoming flat like this. You go more, it will become more flat like this. So literally here, there is no change in concentration per unit time. So understand the meaning of the graph, right? So when I ask you to calculate the rate of this reaction, do you think just by measuring this change in concentration in this time will give you the rate of the reaction? No, because rate is continuously changing. So we talk about the average rates, average. So what is an average rate? The total change in concentration. This is initial, this is final. Final minus initial divided by total time taken. And we have to take one negative sign here because disappearance, it is disappearance. So this final minus initial is also negative, negative, negative. You'll get a positive answer, isn't it? Atharva, is it clear? Dhruv, we are there? Good. So you can calculate the average rate. Now this time I'm asking you, okay, what's the average rate of starting from 0 to 400? So you will take this as final, this as initial divided by 400. But in the question, they can ask anything. They will say, calculate the average between these two values. Average. So it is final. This is final. This is initial. So final minus initial concentration divided by total time, 50 seconds. And every time you work out the averages, you will see answer is different. So what we have to do, we have to see the total time, total change, and that's how we talk in terms of average rate. So this is average rate. This rate which we are talking, the equation which we have understood till now, you will see many equations. This is one of the equation, average. Okay, now let's see. There is another term which generally we are not going to work on it, but is always mentioned in the books: instantaneous rate. Like, for example, when the time is 100 seconds, I want to know at this time what is the exact rate. So, what you do, you make the graph of concentration versus time, and then you drop a perpendicular here at 100, right? Here. Draw a tangent. I said that this will not be in the exam because making the tangent and all these. So all the children, they don't know how to draw the tangent. Many of them, they don't have good mathematical background. So they even don't know the meaning of the tangent. So this question will not be there. So this is the tangent which we have made. Now tangent is a straight line. Tangent, you're aware of tangent, right? All of you? Tangent. This is a line which is going to touch the curve from one point. Like if this is the circle, draw a tangent at this point. So we have a procedure for that. And then you can draw a tangent like this. Not with the help of scale. We need to follow some guidelines by using compass and everything. So this we learn in geometry. And as I said, this everybody is not aware of it. So AP is not going to test you for instantaneous rate. Draw the tangent. Tangent is a straight line. Take the slope of the tangent. What is the slope of the tangent, children? Delta y over delta x. So pick up any 2 points. Like here, they have taken these 2 points, this one and this one. You can see it? These 2 points. And then from this point, draw a perpendicular. From this point, draw a perpendicular. This is your delta y. From this point, draw a perpendicular. Drop a perpendicular. Drop a perpendicular. And this is your delta x, the time 100 here, this one. You're going to take it now this full time. And you will get instantaneous rate. Is it okay? And these instantaneous rates are indicating that the rate is decreasing with the what is here? With the decrease in concentration of Br2, right? The rate is decreasing with a decrease in concentration of Br2. So can I say that rate is proportional to the concentration of Br2? Can I say that, children? Okay. So we are clear about this graphical representation, average rates, instantaneous rates, and their equations. Jyoti? Okay, good. Ready for question? Do this question, please. Read the question carefully. Time zero means initial. Whenever time is zero, just take it as initial. We are talking about initial condition before the reaction started. So it was 1 molar. As the time is progressing, the concentration of H2O2 is decreasing. How the graph will go? See, I'm making a graph. I'll make 2 graphs. You're going to tell me which one is correct. One graph I'm making like this. Other graph I'm making so which one do you think is the right graph of the concentration of H2O2 versus time? Remember, initially there is more decrease in amount per unit time. So this blue graph is correct. The graph will not go like this, that initially there is less decrease, then all of a sudden there is more decrease. See? Analyze the graph, children. I have spent so much time. This is more decrease. This is less decrease. So this graph is wrong. The graph will be always like this. More decrease, more initially, in the initial interval of time. 0 to this. There's more decrease. Can you see the decrease? It's 0.5. And from here to here, it's just 0.25. I think that this is the same time interval. If you take out the difference in time, it is the same interval as it was here. Children, you are getting it? So these questions can be there. They will show you different types of graphs and they will ask you that concentration of the reactant versus time, which graph is good. So this is the graph I have made. Concentration of H2O2 versus time. And I'm saying is going to be like this. What do you think? What can be the graph for H2O per unit time? If I want to make graph of H2O versus time, how the graph will be? Starting from 0, right? It will go like this. Children, you're getting it? So they will ask these type of questions. How the graph will of O2 will be there? Because if 2 moles of H2O formed, how many moles of O2 are formed? Only 1. So the graph will not show you such steep curve. It will be below this, right? Somewhere here like this, less slope because there is less formation of O2. Yusuf, please pay attention to what I'm teaching right now. Answers are simple, okay? Pay attention to what I'm teaching. You missed everything. I was explaining you these graphs. These are questions, multiple choice questions. So pay attention to what I'm teaching. You see that when I show you a question, I'm not interested in answers and I'm not interested straight away you answer the question. I'm discussing everything. I'm trying to make more questions out of it. So I made more questions, graphical questions. So pay attention to that, Yusuf, because you will miss all these things then. We are good with this? Graphical representation of H2O2, then H2O, then O2, right? Now let's see what Yusuf is saying. He's answering A part. So let's discuss. Calculate the average rate of decomposition. What is the average rate of decomposition of H2O2? Don't forget this negative sign. It's decreasing. Disappearance is H2O2 final, which is this. Hold this negative, this one. Final is 0.500. Initial is 1.00 divided by total time taken. This difference 2.16 10 raised to the power 4. Units will be molar per second. And that answer will be positive plus. That is the reason you are taking negative here, so that you get a plus number. We are good with this? Now check, is this answer given by Yusuf is right? Answer given by Yusuf, A part, first answer. Children, please use your calculator. Give me the answer of this question. Atharva, Partha, Dhruv, please answer it. You can put it in scientific notation. So I'm not sure how come Yusuf is getting this answer. The answer is 2.31 times 10 raised to power minus 5 molar per second. So Yusuf, that's the reason I'm asking you to go slow. No, Yusuf. Rate of disappearance is this. You are going to use it to when you're comparing the rates. Now, what is the rate of appearance of O2? The rate of appearance of O2 is 1 by 2. Then you are going to use this coefficient of the rate of disappearance of H2O2. So please pay attention to what I'm teaching and then you can answer the question. You will see you'll be more right then. Now what is this H2O2? 2.31 times 10 raised to the power minus 5. Sami, you are doing calculations? Sami? Yeah, do calculations. Molar per second. Now this answer is also wrong for you. No, Sanvi, I have already shown you calculation. Are you looking at the whiteboard? I've shown the calculation, the rate of disappearance. I'm asking this. They're asking rate of decomposition of H2O2. By definition, rate of disappearance of H2O2 is this. There is no 2 here. Okay, Sanvi? So that answer is wrong. Now the rate of appearance of O2, I can relate it with H2O2. Whatever is the rate of disappearance of H2O2, you divide it by 2. You will get the rate of appearance of O2 because O2 is appearing half time as of disappearance of H2O2. See the ratio 2:1. So that answer will be different. Is it okay? To everyone, Partha? Okay, Jyoti, good. Partha, you are there? Okay. Now can you do this part? This B part. What are these rates? Same rates. So what is the rate of disappearance of H2O2 for this part? Isn't it? Because this minus and this subtraction, this answer will be 0.25 over 2.16 times 10 raised to the power 4. So Sanvi is saying it should be 5.79 times 10 raised to a minus 6. Is it correct, children? This is the answer given by Sanvi. Check it. How come? Sanvi, what are you doing? From where did you get this 5.71? 79. My God. Are you taking 2 again? Are you taking this 2 again? Where is 2 here? There is no 2. So it should be 1.16 times 10 raised to the power minus 5 molar per second. For the second part, right? And what is the rate of appearance of O2? Yes, Sammy, can you tell me what will be the rate of appearance? Can you tell me in words how it will be related to this one? Is it going to be same? Is it going to be double or is it going to be half? The rate of appearance of O2. Is it going to be same as H2O2 or is it going to be half or double? Yes, any one of you? See the relation? See the relation, children? It's going to be half. Very good, Sammy. It's going to be half. Very good, Jyoti. So it is 1.16 times 10 raised to the power minus 5 divided by 2. Are you understanding this now? And that answer will be this. So Yusuf and Sanvi, please understand the rate of disappearance and appearance by definition are the proper that average rate definition. But when you are comparing one with other, one rate of disappearance with the rate of appearance, then you are going to use these coefficients to make them equal to each other. But when you are calculating the rate of disappearance from the data or appearance from the data, then you are not going to include these twos there. Sanvi, Yusuf, you are clear about it? So don't do that error, right? Okay, now factors that affect the rate of the reaction. One of the factor we have already seen. What is that factor? You see the rate is decreasing. What is the factor that the rate is decreasing? The concentration is the factor. Concentration. So this particular slide, I'm going to discuss it very fast. Okay, because this will come again in collision theory in detail, in depth. So right now I'm just giving you a basic idea about the factors that can change the rate of reaction. So pay attention. It's very simple and you all can answer it. This is a container. In this container, these are the molecules. So I'm making it here, these molecules. They are reacting, A reacting to give B, right? So the condition which is needed for A to react, that A and A must collide with each other. They must collide. Collision. So collision is very important. Collision. Are we okay with this? Collision? Without collision, let's take it like this. A plus B giving you C. Let's take like this. It will be more easy to understand now. So I'm making B here. These are B's. So how the reaction will take place? When A and B collide with each other? So collision is very important. So you're going to learn one topic here, collision theory. Very interesting, very simple. So right now I'm just giving you a brief idea. Without collision, there is no reaction. So collision is must for the reaction to take place. So collision depends on the certain factors. So don't you think that if there are more collisions, what happens to the rate? High rate. Agreed? So now whatever factors are going to affect the collisions will affect the rate. Correct? Now let's see. Let's see the factors. Remember temperature. What happens when you increase the temperature to the kinetic energy? We did it so many times. I said it's very important in unit 3 when we were dealing with the gas laws, kinetic molecular theory. This equation I've given you so many times. Memorize it. It's a very popular equation. So as temperature increases, what happens to kinetic energy, children? Increases. As kinetic energy increases, temperature increases, kinetic energy increases. What happens to number of collisions? As they are moving faster, they will collide faster, right? Number of collisions increases. What happens to rate? Rate increases. Agreed? So temperature is one of the factors. You know, you will surprised to know that if you change the temperature of a reaction by 10 degrees Celsius, a change in temperature delta T by 10 degree can double the rate of the reaction. Double. This is very popular statement and observation by the chemist that if you want to carry out a reaction at a double rate, just increase the temperature by 10 degrees Celsius, which is easy. 10 degrees Celsius is hardly any temperature increase, right? Like if you're doing a reaction at 20 degrees Celsius, if the rate is 2 molar per second, you increase the temperature to 30 degrees Celsius, the rate will become the rate will become, children? Answer it. Double 4 molar per second. Answer these simple questions. Speak loudly because they will make you learn things. So we are okay with the factor temperature? Okay. Now this is one factor, temperature. Temperature is one factor, children. Second factor is concentration. You increase the concentration. As you increase the concentration, what happens to the number of collisions? More collisions, more rate. Very good. Dhruv. So easy, right? Sammy? Easy. But then you have to remember these reasons. So concentration is the second reason. So every time you have to think in terms of collisions. More collisions, more concentration, collision is more. Number of collisions, rate is high. Same with pressure. What do you think for pressure? If there is a gas and the pressure of the gas is, yeah, okay, Dhruv, I was coming on that. What do you mean by pressure? Pressure is, pressure is proportional to the amount of gas moles. You remember ideal gas law? Amount of gas, ideal gas law. P equals to N R T over V. If I keep this constant, what's the relation between pressure and amount? Direct. So if you increase pressure, what are you increasing? Amount. If you are increasing amount of the gas, more collisions. So high pressure means more is the amount of the gas, right? High pressure means more amount in less volume. You can say that also. More amount in less volume. More collisions, then they will collide more with each other. More collisions means rate is high. Agreed, children? Rate is high. We are good with this? Okay, now I'm coming on the next one. The next factor is your surface area. If I give you a big piece of wood, very big piece, complete log of tree, and I say, okay, Yusuf, go and burn it, you'll find it very difficult to burn it. But if you chop it into smaller pieces, like this, then burning will become faster. What's the reason? Because for the combustion, you remember that we need oxygen gas. So when you chop it into smaller pieces, then you can see that the oxygen is more touch with the surface. They are more in touch with each other. See, it can go inside these pieces like this. Here, oxygen is just on the top, like this, like this. Only this part is exposed to oxygen. But here, every part is exposed to oxygen. So there is more collision with oxygen. So more surface area. When you divide a big piece into fine powder, surface area increases. That is again geometry. Like if there is a cube, that is also the part of your mathematics learning. This cube, the surface area is 6a squared because there are 6 faces. Every face has an area of length into width. If this is a, this is a. So what is the area of this face? A times a squared. How many such faces are there? 6 of them. So it is 6a squared. But if you divide this cube into 100 small cubes, and if you add surface area of every small cube, you will find that surface area is more than 6a square. Mathematically, you can try it. Okay. So whenever we take a big piece and we divide it into fine powder, surface area increases. There is a mathematical proof for that. Is it okay, children? More surface area means more area of contact. More area of contact means faster rate of the reaction. We are clear about the factor 4. Then there is another factor. Check this reaction. You are aware of energy profiles. I think I have already given you many times. This one. This is the reactant and this is the product. Here is the energy and this is the course of the reaction. Okay, so reactant to product. This is the minimum amount of energy needed. Can you see it's needed? Going up. Endothermic. This part is endothermic. Endo, heat needed. This part. And this is the minimum amount of energy needed. We call it as activation energy. Activation. You don't supply this energy, no reaction. You know, so many things are lying in the nature, but they are not reacting. Why? Because they don't have sufficient energy. They don't have energy which is needed to activate the reaction. Their energies are less than activation energy. So no reaction. If the molecule has this energy only, no reaction. So that's the minimum energy needed. We write it like this: E energy, ACT, activation. Short form, right? Now answer my question. There is a reaction in which the activation energy needed is this much, but there is another reaction. I'm making the another reaction here. The activation energy needed is this much. This is the reactant, this is the product. Which reaction is faster according to your understanding? Otherwise, saying second. What about rest of you if you are listening, all of you? This is first, this is second. Yes, children. Sami, Dhruv, you know, when you are cooking food, in some cooking, we need large amount of energy. Don't you think that that cooking is very slow? Yes. Sami, according to you, can you give me the reason also, children? What is the reason? Because energy needed is less. There's no saturation here, Sanvi. There's no saturation. I didn't use the word saturation. I'm using activation energy word, right? So if the energy needed is more time is needed. If energy needed is less time is needed. Sammy, I didn't get your answer. If you're listening, please type the answer here. And this energy is called as activation energy. Yes, less activation energy. And don't try to copy paste each other answer. Use your own language. So what is the symbol of activation energy? All of you please type the symbol of activation energy. EACT, this one. Yes, like this. Yes. This is as a prefix, but in the type, you cannot write it. So can I say the rate of reaction is higher if E activation is lesser? Can I say that, children? Yes or no? This one, write on this statement. It's very important. Plenty of questions are there. Now you heard about catalyst. Sammy, what do you know about catalyst? What a catalyst can do? A catalyst can increase the rate of the reaction. It can increase the rate of the reaction. But how? Rate of reaction. There is a topic, last topic of this unit, where you are going to learn only about catalyst. They they speed up the reaction the way Sanvi is using the language. Sammy, yes, very good. And Sammy is giving us reason. And that is the reason. When you add a catalyst in a reaction mixture, it lowers the activation energy. Perfect, Sammy. Good understanding. It lowers the activation energy. So now you see this A and this B. Now which one is faster? A or B? B is faster. Why? Low activation energy. And if you see, this is the same reaction. Same reaction. This is the reactant and this is the product. Same reaction. And same energy profile. But there are two energy profiles. One, A is without catalyst. B is with catalyst. So very good, Sammy. So children, memorize this. A catalyst lowers the activation energy, and that's how it increases the rate of the reaction. Yes, Dhruv. So that's why the rate of the reaction in our biological system, if you remove these enzymes from your biological system, which are catalyst, your metabolism will stop. Nothing will happen because all these reactions inside our body are taking place within seconds, microseconds, so fast. Why? Because enzymes are there, enzymes. And what are enzymes? Biocatalyst. Biocatalyst. They are proteins also. That's why we say proteins are so important for us. Proteins are enzymes, or enzymes are proteins. And these proteins, enzymes, generally enzymes you call them, because proteins are of different types. So one category of the proteins is enzyme. These enzymes are biocatalyst. If you remove these enzymes from the biological system, your metabolism, breathing, everything will stop. Your that biological body will stop working. It will collapse. Yes. So is it clear, children? So what are the factors? I'm showing you the factors here. Temperature, concentration, catalyst, surface area, and pressure. 5 factors, right? I've discussed in detail all these factors. So I'm not going to give you more time on this. I want to move on the next topic. Next topic is Introduction to Rate Law. Okay, children, if you remember from this graph, this one, remember we did this graph? And I said from this graph, it appears that rate is proportional to the concentration of Br2. Isn't it? We said this. See, as the concentration of Br2 decreasing, rate is decreasing, correct? So when you remove this proportional, then you can say rate is equal to K times concentration of Br2. What is K? It's a constant of proportionality. K is a constant. But this K has a very specific name. It's a small k, children. It has a very specific name. It's going to trouble you a lot in the exam and here in kinetics. So start liking it. Make it as your friend. Understand it properly. What is K? Rate constant. Rate constant. You're going to learn one Arrhenius equation based on this K. So if the value of K is high, what happens to rate, children? K value is high. What happens to rate? Rate will become high. But generally for a particular reaction, like for this reaction, for a reaction, This K, please write down this also. K has a constant value at a constant temperature for a particular reaction. Constant value at constant temperature. So who can change the value of K? Who can change the value of K? K depends. K, rate constant, children. Rate constant depends on temperature. You change the temperature, K changes. It also depends on activation energy. Activation. You add catalyst, activation energy goes down, K increases because rate increases. So this we are going to discuss in detail in Arrhenius equation, right? So the rate constant is clear. And the way I'm representing this equation now, see earlier I said rate equals to minus delta Br2 over delta T. I said this. Now I'm saying rate equals to K times concentration of Br2. This is called as average rate of the reaction, average rate, average rate. And you know, this form is called as rate law. That is your next unit, rate law, or next topic. Is it clear, children? We have understood today average rate, instantaneous rate, how to relate the rate of appearance and disappearance. Now we are moving on to next method of expressing rate, and that is called as rate law. Introduction to rate law. So what is rate law? According to rate law, if there is a reaction like this, first remember, rate law is always in terms of the concentration of the reactants. So for this reaction, I can write down rate law as rate equals to the rate constant K, which depends on K depends on two factors. All of you, please type it. Rate constant depends only on two factors. Yes, children. Temperature and activation energy. Keep memorizing it because you are going to learn this in detail later on. So you change the temperature, you change the reaction, K changes, right? You add catalyst, K changes. Concentration of A raised to power X. Concentration of B raised to power Y. This is the rate law for this equation. So rate law is always in terms of the reactants raised to power some coefficient, which is not this. It's not A. I've not taken coefficient of the balanced equation. Some coefficient by Y, which is not B. Now what are these X and Y? These are called as order of the reaction. What are they called as? Order. Like X is the order with respect to A. Y is the order with respect to B. But now the question is, what do you mean by order? So I'm going to explain you that. Are you okay with the rate law? So for any reaction, like for example, if I say H2 plus 3H2 plus N2 giving you NH3, then what's the rate law here? Rate law for this reaction. K, the rate constant, concentration of H2 raised to power X. Don't take this 3. This 3 and this 1 has nothing doing with these orders. Concentration of N2 raised to power Y. But how will I come to know X and Y? Experimental data is needed. Experimental method. Experimental data. So ready children for this order to understand the meaning of the order? Ready children? You have understood how to write down the rate law for an equation? Rate law is always in terms of concentration of the reactants. Never write in terms of the product. Remember, average rate can be in terms of the product or reactant, rate of appearance, disappearance. We were discussing that. But rate law is always for reactants, never for products. Okay, one thing. Second, every reactant has a specific order. We need to understand the word order. Ready, children? Okay, let's understand. Let's say this is the reaction, this one, constant, and this is the rate law. Now I'm performing an experiment. In the experiment, I'm measuring the concentration of A and B. Initially, in experiment 1, A is 2.0, B is 2.0, and the rate is 4 molar per second. You know the units, molar per second. This is molar and this is molar. This is the experimental data I have. Experiment 1. In experiment 2, I double the concentration of A. I'm doubling the concentration of A, keeping the concentration of B constant, no change. And I found the rate is now 8 molar per second. So as I double the concentration of A, the rate is increasing by 2 times, right? You increase this by 2 times, check. You increase this by 2 times, this is also increased by 2 times. That means X is equal to 1. Order is 1. Because it's 1:1. Correct? Children, you're understanding the meaning of order? Okay, let me give you another experimental data. Now let's take third experimental data, 2.0. I have made B as 4.0. And I found the rate as 16. Now compare 1 with 3. Just ignore this one. The center one ignore, because in the center A is changing. Just check A first and second. Is A changing? No. Is B changing? Yes. How many times? 2. So this rate is changing. This rate is changing because of the change in B. But this one is changing 2 times, and this one is changing 2 raised to power 2 times, 4 times. Isn't it? So what is the value of Y? Y is 2. So what's the rate law for this reaction from this experimental data? That rate is equal to K times concentration of A raised to power 1, concentration of B raised to power 2. If still you're confused, I'm just trying to make you understand the word order. Order means when you change the concentration of one of the reactant, what is the effect of that change in concentration on the rate? So mathematically we calculate that. If we double the concentration, rate is doubled, then it's first order. But if you double the concentration and rate has become 4 times, then it is second order. But if you double the concentration and rate has become 8 times, 8, then it is third order, like this. Are you getting the meaning of the order, children? Ready for one question before we leave the class? Is there anyone struggling here? Sammy, everything is okay? Look at this equation. Can you give me the rate law? Rate law for the above equation in terms of X and Y. So first you write down the rate law. I'm doing this question Please ask your questions in case you are not clear. So I will say rate equals to rate constant K, concentration of F2 raised to power X, concentration of ClO2 raised to power Y. That's the rate law. What's the aim? Aim is to know X and Y from this data table. If you look at experiment 1, experiment 2, these are the rates. Let's say this is rate 1, rate 2. Please understand this, children. What is rate 1? Rate 1 is K times concentration of F2, which is 0.10 raised to power X, concentration of ClO2. I'm taking data from here. This one, 0.10 raised to power Y. This is rate 1, which is equal to 1.2 times 10 raised to power minus 3. Now, what is rate 2? Rate 2 is K times 0.10 raised to power X, 0.040 raised to power Y, which is 4.8 times 10 raised to power minus 3. Now you take the ratio of this rate 1 and rate 2. Take the ratio. So rate 2 divided by rate 1. Plug in this value in the numerator. I'm taking rate 2 above because this value is higher. Divided by like this, which is 4.8 times 10 raised to a minus 3 divided by 1.2 times 10 raised to a minus 3. Cancel the things which are same. See, I generally cancel here only. Right now I'm giving you proper method, but very soon you will learn a shortcut also. So this is cancelled. And what is this? 4 over 1 raised to power y. And what is this, children? 4. 4 raised to power 1. Bases are same. You remember we discussed exponential mathematics in unit 0. So what is y? Y is 1. So this y is 1. Similarly, you can take the ratio of the rates of experiment 1 with experiment 3. Now here I'm going to show you the shortcut. Now ClO2 is not changing, cancelled the way this is cancelled. This one, they cancelled. What is happening to the F2 is doubled. What is happening to the rate is doubled. So what's the value of X? That is also 1. 2 raised to power X is 2 raised to power 1. X is 1. So what's the rate law? K times concentration of F2 raised to power 1, ClO2 raised to power 1, like this. Okay, children. So that was the story about the rate law. And in the next class, please come prepared. I'm going to discuss only questions. You see, if you can see my presentation here. Now only questions are there. Questions. These are questions. So plenty of questions on the rate laws. So please come prepared. Review it properly before you enter in the class. So I'll see you in the next class. You're welcome. Bye-bye. If you have any questions, you can stay back.